Welcome in this new Rebel tutorial. My name is Gabriel Neville, I'm an FX lead at MPC, and today we're going to learn how to do this disintegration effect. First, we're going to look at how we can art direct our mask destruction with clusters, procedural animations, and particles. Then we're going to go through the different secondaries we can add, like smoke, pops, vector debris, and flames. And then to finish, we'll have a look at creating custom AOVs and tech passes to have more control during the composting phase. Let's hop in. Okay, hello everyone. So welcome in this tutorial here. This is the template scene that I prepared for you. So we have basically just going to go through the different elements that we have. A few render elements here. The camera, the lights. So we have both Mantra lights for viewport and actual Arnold lights for render. We have here the geometry. So we have the mask, the human, and the robe. Here's basically where we're going to put all of our simulations. Here we have the shaders and the output. So we're just, this is basically where we're going to render stuff. So that's basically for the presentation. I'm currently using Houdini 19.5, and we're going to use Arnold for rendering. And yeah, that's about it. Let's get started now. So basically, if I just switch back to auto update, the first thing I'm going to do, so here I can read my animations. Those are directly Alembic. And if you see here in the mask import that there's just like this small compute transform, something that we're going to use after to attach our simulation. So here this is the rest, and then after this, it's calculating a point here with a bunch of information on it. Alright, so I'm just going to switch back to animated. Here, if you want to get the geometry spreadsheet like me, very easy, you can just, I'm going back to the build here. So you can do here split tab, top, bottom. So here, you see we have two scene view. Obviously here I don't want the scene view, so I'm going to click on the plus, new pad type, inspector, geometry, spreadsheet. I close this one, drag it down, that way I can just see my attributes here. And we can do the same here with, we're going to split left, right here, in this case. And I'm going to give those numbers right here, 1, 1, 2, and 2. This is going to make stuff way easier to just drag and drop stuff, and then I can actually, after this, I can save this build. So you can call this build once screen split. For example, you can name it as you like, and here you will be able to directly select it here. Cool, so that's it. Now let's create this effect. So here, yeah, we're going to pass you those textures. The reason why we see them in the viewport is that there's already something assigned to it, the shop material path, and it's going to be referenced in the shader. This mask, and there's a small toggle that allow you to see it in the viewport, even though if it's an adult shader, which is pretty helpful. All right, cool. So now I'm just going to go to FX working in my case. You don't have to do this, but just for me, I like it. It's getting a bit more organized. And I'm just going to call main integration. All right, amazing. And I'm going to object merge and drag and drop the mask raspos. All right, cool. So this one is the static one. Is it? All right. Yeah, this is the static one. And we have like here two groups. So I'm first going to split this group. And here we have the inside and the outside. We will not work with the inside on this disintegration, but we'll use for something else. So I'm just going to click on invert selection, and here I'm just going to call this outside, and here inside. Okay, amazing. So I'm going to continue working with this one. Now, if we have a look at the topology of the model, so we can see that the topology is not ideal because it's pretty, it's not very uniform, and the best, obviously, of course, we want to avoid uniform stuff in effects, but here the best is first make it uniform and then break it up with more control. So we're going to do some remeshes, but first, what we can do, we're going to use the node called the vertex split. And the vertex split is actually just going to help us maintain those UVs after a remesh. So we can actually see if I were to use this remesh here. Not bad. See, like the texture is holding up if I just remove it. You can see that the UVs are getting crazy. So let's just keep it. And here in the target size, I'm gonna go for something pretty small. So it's gonna be this value, 0.005. And actually, I'm going to cancel this just now, and I'm just going to create a file cache. It's going to be non-time dependent. So I can untick this. Here, something that can be useful is going to create a $cache variable. Obviously here, like, you know, we can do our $job. That is already set it. Don't forget to set it in your own space. It's pretty useful. But like basically, if like me, you have like different disks, so SSDs and HDDs. Usually, like you want to store your caches on like another disk and work with the SSDs. So basically, you can just type cache and basically just point it where you want it to work. So here in this case, you know, this is going to be D and E for job. So like those have the same structure, but they're just going to be on a different disk. And for my case, I'm just going to put for tutorial. Okay, and so here at base folder, I can use this $cache that we just created. You can see it's working. And here for the base name, we like $OS. And here we're going to call this fake remesh. Oh, amazing. And then I can click to save the disk. And so here, this can take like a few seconds, depending on the performances of your computer. But it shouldn't be that bad neither. I think we should be pretty okay. All right. So now it's done. Going to switch to its updates. And here you can see when by the way, here what you see, I just press W and it's going to switch to wireframe. And so here we have like a nice uniform and dense topology. So it's going to be great for us. Only triangles, and yeah, so that's it. So basically now the whole principle of the disintegration effect. Basically, each face, each primitive is going to be a point that is going to move in space, and then we're going to assign different clusters and all this. But basically, to avoid any fracturing, we're just going to make every face independent. So here, if I were to put an exploded view, just to illustrate a bit this, we can see that the connectivity is going to be exploded based on connectivity. In this case, this is the current connectivity. What we want to do, we're going to put a faces node, and we're going to put unique point. And now you can actually see that all those primitives are individual islands, which is what we want, because then it's going to be easier for us to just group primitives and then transform them, so make them blow in the wind. Cool. So there's here unique points. Amazing. Now we're going to store an attribute called prim_id. So I can just do prim_id equals prim_num, which is a Houdini attribute. And here, if I switch to point, I can see that every prim_id, every point has like this attribute. So basically here, for clarity, I'm going just to put on the grid. And we can just review this. So here you can see you have like a bunch of points and a bunch of primitives. So obviously here each point has several primitives. So here, for example, point 25 is shared between primitive 13, 14, 22, 23. So in this case, it can create confusion, right? But if you just actually do this unique point technique, we'll actually see that now each primitive has unique points. So like you will have 4 points here, and it will only be attached to one primitive. So that's why we can actually just do this very simple prim_id equals prim_num, and basically we're storing the information of the primitive to the point, so each one is going to be attached to it. Alright, so I'm just going to store this prim_id, and alright, I'm just going to turn off the position here, and now basically we're just going to extract transform. So what I mean by this, basically now, remember when I talked about having 1 point transforming the primitives? Well, basically that's what we're going to do here. So if you do extract transform, you can actually just put them to the same inputs. You can see here, we just have 1 point. That's not what we want. We want to specify a piece attribute. And here our piece attribute is going to be prim_id that is stored into points. And now I can see I have a bunch of points. So actually now, this is pretty interesting. Like, we were like at 4.6 million points, but 1,500,000 primitives. And now we have 1,500,000 primitive points actually. So like you can see that we switch, like now we have the number of primitives in the points and no primitives whatsoever. So this is pretty useful. Like the good thing here, you can see that Houdini created for us those orient attribute and pivot attribute, which is going to make us able to transform pieces. So here, if I just were to drop down a transform pieces node here, and I'm going to put prim_id instead of name, and basically here, if I were just to put some noise, so we can create one small attribute blob here, turbulent noise that is taking the position as an input and putting this in the color. I'm going to right click, create input parameters. Okay. And basically, if I use this node to translate our point, so here, it's like our multiplier. And I'm going to translate this in the x-axis, dot x. And I'm just going to clamp the color so it doesn't go on both sides. Okay, so you can see here, I'm kind of displacing those points. But the cool thing is, by doing so, we actually were able to deform the geometry, right? So you can see that everywhere where like the noise is black, we're not moving it. But everywhere where it's white, we're moving it. So this is a good way to be able to work with just points and transform our geometry. This is the base principle. All right. So basically now I'm just going to drag and drop this pretty long. And here we're going to work like this in parallel on this point cloud. So obviously those were just for tests. So I'm just going to put test offset. And here test noise. I'm going to keep them for the end. And actually, I'm just going to copy paste this attribute up here. Okay. So basically now, as you can see with this small test, here we're actually, we can see that those, we have something pretty uniform in terms of size. So we have either those big pieces or like those are very, very small pieces, because basically they all have different values between the triangles. And you can see that we have something that looks pretty uniform, right? So like we just have a bunch of points, and what we want to do now is create clusters. So clusters are going to be like those kind of big pieces with different size, and like we're going to work on getting something a bit more appealing to the human eye. So here, yeah, I'm just going to create first a rest position before this test noise. And actually we're going to transform this noise to a displacement noise. So we're just going to put an add and add this one in the position instead of the color. We're going to switch to 3D noise. And we're going to make it pretty small. So in our case, 0.01. All right. We're going to call this displacement noise. And so you can ask me, why am I doing this react and displacement noise? Well, it's actually because we will want to break up the clusters. So if I were to bypass this, you can see actually I'm going to put a blue cluster. And I'm going to remove random detach because that's not what we want. And here in our case, I'm going to put something a bit smaller, so 0.04. Cool. So you can see here in our case, this cluster is actually creating based on the Vor noise. So it's basically scattering points, and then basically based on distance is going to get to the closest island. So in this case, you can see like the Vor noise is very powerful, but the problem is like usually it looks a bit simplified because like we have very straight edges, right? Like that's the same algorithm as if you do the Warner fracture. So like all those very clean edges, the structure that you saw usually come this way. So the good thing here, we're creating rest position. Rest position is going to store the position into another attribute. So if I just were to hide all attributes, put P and rest, you can see that those are actually just exactly the same. So we want stores to be able actually afterwards to put back the correct position. So if I write after p equals back to rest, you can see that now we have something a bit more broken up. So here the trick is to displace the noise, do our clusters. So you can see here that we have like our very straight lines again. But then when we put it back, now we have something that looks way more organic in terms of distribution. I mean, more in terms of edge detail. So I'm just going to call this one back to rest. And so it's working pretty well. Just the thing now is I don't want them all to be the same size. So I'm going to right click, allow link of contents. And in here you can see that there's a small wrangle here. And basically we're just going to create another seed. So I'm just going to copy this here, this line, or I'm going to copy this here. It's going to be C2. And basically here is going to be C2. We're going to add the two together. Okay, something happened, more or less the same for now. But basically here, we're just going to create a different frequency multiplier to get something more different. I'm going to click on this to get the parameter down, and then I'm going to press on 2. So we can see that now we have something a bit more broken up. You know, we have like still some bigger chunks and some smaller ones as well. So yeah, I think like, you know, this is good values for like our big pieces. All right, so now basically I'm just going to create a name attribute. I'm going to call this cluster name. And it's going to be cluster plus ITOA. And you could put here cluster directly. But basically it won't work because our cluster attribute here is a float. And here ITOA is expecting an integer. So we're going to generate a random number based on this one. So we're going to do random h, and we're going to close the parentheses here. And now if I were to put cluster name, you can see I have all those values. We have some negative values here, but it's fine. It's like a string anyway, so we don't really mind. And here I'm just going to cluster name. Cool. So basically now we're going to make sure that we have that all of our clusters are actually independent. So here, if I were to take the exploded view and put cluster name, you can see that this is like this. Those are like treated now as individual pieces. The thing is, sometimes like the noise will take two pieces that kind of are in the same way but are not exactly in the same place. So if I were to do for each name primitive in this case, I'm just going to try to find the one that could illustrate that. cluster name in the point. And we're going to switch to single pass. So here they all look pretty much independent. Already here, this one, see, they kind of are not supposed to be a real island, right? Like you would like try to divide those into either 1, 2, 3, 4 different islands, but not just like one single one. This one, same here, like, you know, we would expect to have like a smaller island here, and a bigger one for those. Those are like, yeah, this is like a bit more extreme as well. Like, you know, you would really want those Neville ends. The reason why is because otherwise we might get something a bit funky. If here in this case it's actually okay, but like if we get like pieces that are pretty far from each other, the centroid of this point and the rotation pivot is going to be in the middle and is going to create some issue. So yeah, basically we're going to create a subnetwork. I'm going to connect it. And I'm going to keep this for each actually. Okay. So now we have our points. I'm going to make those points a bit bigger now. Okay. So how do we tell Houdini, please do not put them together? Well, first we're going to try to turn them to PDBs. So now they're super big. Obviously, that's not what we want. So I'm going to here reduce the voxel size and refers to the size of those points. So here you can see that those disappeared, and it's because basically here the p scale is smaller than the voxel size. So we would want to try something fairly small. And here, this is what we have. So it's actually pretty helpful because now, just with this, we could actually identify the connectivity here, and that, like, you know, we would have 3 islands. So we could actually do PDB segment by connectivity. And this is what it gives us. So now, like, you know, we have those 3 clusters. Obviously, we don't want to work with this. So we're going to convert PDB to polygon. And you can see that they now have attributes. So we have surface 0, surface 1, surface 2. I can try to select them. So if I put the blast on the viewport, press 9, filter by name, you can see surface 0, 1, 2. Great. The problem here, we're working with points, so I'm just going to ask him to promote this 2 points. So attribute promote from primitive 2 points, and we're going to promote name. All right, so as I said, we're not going to directly work with this, we're going to keep the points. But we're going to do something with it. And actually what we're going to do, we're going to add a suffix to our name. So basically here, we're going to do a simple near point. So we're going to store the near point number into an integer called near pt. And we're going to use the near point function. I'm going to press 1 because I want to have a look at the second input. And I'm going to put the actual position of it. Now we're going to try to find the name of this neighbor. So we're going to call it name, let's say. And it's going to be 0.1 because we're looking at the second input. And we're going to call this name because we're looking for the name. And the point number is going to be near PT. Cool. So now if I were to do cluster name plus equal comma plus name here, if I were to look at those cluster name, you can see that now they changed. Now we came from having a single name to different names, which is great for us. So if I were to do a color, random from attributes, I'm going to put cluster name. You can see that now a bit hard to see, but yeah, like they all have different color, so they're like individual clusters. So basically here, this is just the small phase where we just want to make sure that we're working with individual islands. Here in this case, you know, like even though it's not really connected, you can actually adjust the threshold. You can do something a bit more precise if you want, but like it's just to make sure that we don't have clusters that are very far apart. So that's the whole idea. Here also, we do something we can try to do. We can just try to reduce a bit the size of this string. So to do this, we can actually just do not string split, and we're going to use the split function to look for this name, and we're actually going to, our separator is going to be this closing parentheses. And so here now we have a list of all the different split, and you can actually that surface underscore 0, and so basically surface will be the first index in this list, and 0, so the number, that's basically what we want. So it's going to be 1. So I can basically just say plus split 1, and you can see that now we have this underscore 0, 1, 2, 3. So it's working pretty great. Obviously here I'm still in single pass, and now we will need to do it for all those pieces. So something to, here I'm just going to find, and let's just name. Something that works pretty well with for each is compile block. So those are going to create like those yellow thing on top. And it basically is just going to allow your computer to use multi-threading. So you just need basically to do this, type multi-thread when compiled. And of course, you need to just make sure that we don't have anything that can't be compiled. So you can press D, context-specific badges. I'm going to go to normal or large even. And here, all of our operations are compilable, so we should be good. All right, and this we're going to call this unique clusters. Just going to hide those inputs. I don't want to see them. All right, cool. And here I'm just going to copy this file cache here, and I'm going to call this main cluster. I don't know if it's a Houdini 19.5 thing, but basically we just need to put $OS each time. It's a bit annoying, but so now if I do save to disk, obviously we just have this one. It's working. So now I'm just going to remove the single pass, and I'm going to bake that again. It was fairly fast. And now it's time for comparison. So we have 1502 different cluster, where before we had 1037. So it actually divided the clusters quite a lot, but like, you know, all those kind of individual pieces, just make sure that they're not, like here, for example, the blue, I can see this one being the same cluster, so now they're going to be divided. To actually check that, we can actually put another color. We're going to just copy the one that we made here. Obviously there's a different seed as well, but sounds about right, let's say. Cool. Obviously here, if you want something a bit more sampling, you can actually reduce the size and get something with smaller voxel size, but in our case, those values should be more than enough. And so here we're just going to put a null called in big cluster fast. All right, amazing. So obviously here, just going to go to the dark background again. Here, still nothing changed, you know, because it's not because like we added those clusters that now in our small test, anything has changed. But basically here, the principle is going to be something a bit like this. So just for a test, I'm going to promote the color and I'm going to average it per cluster. So if I were to do that, I can just select the color, and as piece attribute, I can type cluster name. And you can see that now all the cluster name have the same color value. And so for now, we can switch between minimum, average, or maximum. In our case, I'm just going to keep it to average. And then you can see that just this small thing, boom. Now we have something that looks like actual individual pieces, you know, and not just those triangles flying everywhere. So this is going to create something a bit more interesting for us. So, you know, you can see that when I scroll, those pieces are actually moving. All right, so that's great. That's our small tests. I'm just going to put a small sticky note here. It's going to be first clusters. Let's go. And I'm still going to continue on those points. Can do this. First or big clusters, actually. Okay. So now we're going to work on the propagation of the effect. So how and when those pieces are going to get moving, because we want to animate that. Let's get started. All right, so now this propagation. So to do that, I'm just going to create a sphere. And I'm going to place it where I want. So here in this case, I already have the coordinates. I'm just going to copy it. This is basically where I want it to be. On the right side, near the jaw of our mask. So now basically I'm just going to create a point from volume. And here I'm just going to fill up this sphere with a bunch of points. So we don't need that much points. It can actually just be this. Let's just create a nice polygon mesh. All right, so now we have those points here. And it's going to be fairly simple. Here in this case, I didn't need to do any custom growth or anything. It's just a good old attribute transfer. So we're going to transfer here the color to visualize it. So I'm going to put a color that is black and a color that is white. So everything here, when you see the color, everything is white because we have a distance threshold way too high. So I'm going to actually remove the distance threshold, and I'm just going to play with the blend. So the values that I had that were kind of working for me were actually 0.13. I'll click on the last frame, and then the first one was, I don't know if it was 0 or 0.02. All right, cool. And now if I shift click, I can actually see the curve. So here I have something that it's the ease in, ease out default. Usually that's something that it looks very CG because you have something that starts slow, goes fast, and then ease out. So that's basically not the type of curve that we want in our case. I mean, like you could keep it, but like we could try to switch it to ease in. Then we have something way more progressive at the beginning, and then after it goes a bit faster. Cool. Sounds like a plan. Now I'm going to keep my test noise here. I'm just going to keep it here. And I'm just going to call this propagation noise. We're going to break this color by multiplying it with by noise. So here in this case, we're going to keep 1D noise, but we're just going to multiply it. So we're going to take the color as first input, our noise second input, and the color here. And we're just going to clamp our noise just so we don't have negative values or values above 1. The noise type is going to be sparse convolution. And here for the frequency I had 37.7. And I'm just going to do copy parameter and basically paste relative reference on those two. That way, like, we know that we have uniform noise. And here in the offset, I think I just have this small 1.9 offset. The roughness, I also tune it down to something a bit more soft. And yeah, that's about it. So that's our animation color. Cool. Obviously, we're going to multiply this noise, this color, by keyframe. So we're going to put this amount of this color into something called amount float, and here we're going to multiply this float by something called a child float called animation, and then after we're just going to export those attributes. So amount, and we're going to put this in CD again. So here you can see that I can just animate my noise. I could have animated directly here, but I just prefer this to do this a bit separately. So here, obviously, we're going to start at 0. And after on the last frame is going to be 1. I'm just going to check which frame that put it. That's going to be 1 here at the end. And so from 1. And in here, same, we're going to switch to is in. Cool. So now if I were to play this, you can see it's something that is slowly turning out white, and then there you go. So a very simple animation here in this case. And we're just going to call this propagation. Cool. And I'm just going to create like another name. It's going to be for later. So I'm just going to create this name equal cluster name. So here I'm just copying my string in this cluster name thing. All right, so obviously now if I were to remove this noise, you can actually see that our animation can actually see that it's kind of working now already. You know, we have something that goes into a direction. So like, you know, that could be a good way to prototype our effects. Obviously here, bunch of stuff that could be improved. And yeah, the first one is gonna be try to get more feeling of a bending rather than just the pieces moving and attaching. So to do that, I'm going to take the input geometry. So here I can just take here, go to in geo. All right, take this. And I'm going to attribute copy the CD. So the opposite. Based on frame ID. So we have this. Here, obviously, something doesn't seem to match. Or to display the color. Okay, there's something, it's just not very visible in the viewport. Yeah, okay, so because there's the texture. Here what we can do just to remove the texture, in this case, we're going to remove this show material path. And yeah, okay, now we see that the color is probably transferred. Cool, and then we're going to do the same, but just with a fused version of it. And we're going to be very, very subtle on the fuse. All right, cool. And we're going to do the same thing. Copy the color. So basically here what we're going to try to do, I'm going to try to deform this one based on this one. So like the only two difference here is that, like, you know, if we were to do like this include view thing, those are like a lot of different. This is just one big chunk. Cool. So basically now what we're going to do, we're going to create a wrangle. So like both, this is like the rest position. Rest deformer. And here we're going to create the animated deformer. Cool. And here in this case, we're going to create a vector direction. We're going to normalize this vector, and we're going to create a channel vector. So basically, this is going to be the direction of where we want to push our pieces. In this case, that's something that is one and one in those axes. And here I'm just going to do p plus equal dir time clamp cd.r 0, 1, and I'm going to multiply this by a multiplier melt. And here you can see that it's kind of working. So basically you want to, we can just like put this basically on the left frame. This sounds like a good amount of displacements. And here the idea is that we're going to point deform it. The reason why we're not point deforming the points themselves is because they will not capture any they will not capture any of the rotation and that we're trying to do here. So here you can see that it's not very interesting because we go from here to this, so it's more or less our deformer, right? So what we want to do a bit in this case actually here, instead of copying the CD, we're going to copy the name, right? And from this name, we're going to promote it. We're going to time shift it. So just so it doesn't become time dependent anymore. And we're going to promote name to primitives. All right. And now we're going to create pack primitives. So we're going to remove create name attribute to just create pack geometry. So now we have our clusters, right? And basically now, this is where the fun stuff happened. You know that when we were not in pack primitive, we had something very stretchy and all this. But now that we're back on those, like now that we're in pack primitive land, we're keeping some of the nice bending and rotation. You can see that it's trying to match it the best you can, but we have those rigid pieces. So this is basically now the first real time you can see our effect here. All right, cool. The thing is, like, we don't want to work with pack primitive. So I'm just going to extract transform, and I'm going to extract from the rest position, so the reference geometry, to the target one, and we're going to do the point one. All right. And now if I were to do a switch and evaluate what we have here, I can see that it's not working anymore, it's still broken. So here what we actually want to do is transform our old point cloud. So we're going to take it here by this animation here. And then we can see that we have our point cloud that is moving the way we want now. All right, so this is great. And now when we transform pieces, we have something that matches what we want. All right, that's great. Now I'm just going to create an object merge here, and I'm going to take our mask transform, and I'm going to transform pieces here in the middle, just after the point of form. You can see here before it was static, now it's animated. And if I go back to the non-packed primitive with the textures and all that, but something's working, so yeah, this is great. And you know, like by just actually changing the cluster, we can get different pieces and all that. So it's like our base animation here. Obviously, we can work a bit more on it. First, something that is always helpful is to compute the velocity. So that way now you can see that we do velocity vectors that are directly transferring into the geometry. And we can also maybe add some dimensional rotation. So when the pieces are far from the rest of the mask, it could get, a bit more rotating and a bit more organic. So to do that, we're going to create a small wrangle here. And we're going to do a time shift. We're going to take the last frame, and I'm going to put it in the second input. All right, so that's great. For all this here, the only thing that we didn't really generate was our color. So I'm just going to take back the propagation here, and I'm going to actually copy this color back to those points, matching our cluster name, sorry, attributes. And here actually in this case, we can actually just say name. Okay. So now we can see that we do have the color that's we transferred. This is great. And basically here the color is also going to drive the amount of additional rotation that we're going to do. So I'm just going to take this. And I'm going to start writing stuff. So basically, first thing we want the amount of rotation that we want to know is going to be based on the color, but like we're going to remap it with a ramp. So I'm going to create this ramp and see that R is going to be our amount. Then as well, like to rotate stuff, basically we're going to create quaternions, and so to create this you need a vector and a float. So we have our float, the amount, and now we need our vector. So how along which vector do we need to rotate those pieces? So I'm going to call this nvel, and I'm going to take the velocity on the last frame, so that way we avoid having changing velocities. And I'm just going to look for ptnum. It's a constant point count, so it's working. Cool. And then we're going to create a vector for, so quaternion, call rotation, and yeah, here, spoiler, quaternion again, and we're going to convert an angle, so a float, times the amount. This is the amount is going to be the animated one, so based on the color. And then we're going to normalize our nvel. So this is the vector that I talked about. Cool. And here, small, put one here as well. Okay. So here, if I were to change the angle, nothing happens yet. And it's because now we need to modify our orange. So you can see here that if I look in this, we already have some orange attributes. So we don't want to override it. We want to transform them according to this vector and this float. So to do this, we're going to do something called, we're going to use Q multiply. So it's going to take our orient and make a move to another according to another quaternion. So now, if I were to do this, even if I look at the you can see that some stuff are moving, right? Cool. So basically, I'm going to keep it around 200. And here, like, we don't want something uniform, so we want something that's a bit more Bezier. So we can change a bit the interpolation of our ramp. And here we want something, yeah, 0.33. And that's the low value. So basically we're going to avoid doing any rotation on the pieces that have low colors, and then when they have more colors, so that means they're more far from the mask, and then we can add those additional rotation. All right, cool. So now I propose that we just do a small flipbook, and to do a proper flipbook, we're going to first hide the mask. So I click here, and I can just make sure that I don't have any custom resolution baked. I can just start. All right, cool. So this is what we have now. The flipbook just finished. So yeah, like what's particularly nice are like the beginning, like the first frames of all this. Obviously we have like some collision issue and all this because it's procedural effect for now. But like it's good. Like this we have this kind of bending that we want to get, and then after when they continue to get advected, you can see that some like the stuff continue to rolls and rotate. So for now we're pretty good. Basically now the main thing is going to be trying to get more detail out of it. So we will want to try to get something a bit more broken up between two big pieces. So we're going to do this with cluster all again. So here, yeah, we're just going to organize maybe a bit our scene again. So here we're just going to call this propagation. And then we're going to call this animation big pieces. Okay. Here and those drop boxes. Okay. So now what we're going to do actually is I'm just going to just we're going to create those second small clusters. So we can create something on the side here, small clusters. And we're going to take our big clusters. And we're going to copy paste our few of our nodes actually. We're going to copy paste the displacements, the glue, and the back to rest. All right. Obviously here we're going to change the size of it. So we're going to go down to, let's say, 0.07. All right, here you can see that nothing changes. So we're going just to do an attribute delete, and we're going to remove the actual cluster attribute. And now you can see that we do have something. All right, 0.07. Not too bad. Maybe here the displacement amount is a bit too big, so we're just going to reduce it. Let's increase a bit the frequency. Got this. Cool. So like those are now the our smaller clusters. So basically here the idea is that like like if I put those two, each cluster is going to be composed of several smaller clusters, and those smaller clusters are going to be deformed and at some point activated. So So this is good, and we're going to create an attribute called cluster name 2. So cluster name 2 equals cluster plus like blah, blah, blah. It's going to be the exact same thing as before. And actually we can even put equals cluster name plus underscore plus this thing. So here something is not working. Okay. So you can see now, if I go to cluster name 2, so the same thing, but they have like an additional float behind it. Great, so I'm just going to call this cluster name 2. And basically the size is good, but like we would want a bit more variation on this. So what we're going to do, we're going to split like this. Let's say it's going to be our mid-size, and now we want to do like the very small ones. So the very small one, to do that, we're going to split this in group. So we're going to do a random based on our cluster, and we're going to add a seed. And if this random is smaller than threshold, then we're going to put the color for now. So let's do CD set. We're going to put it red. All right. We can move the seed, and then like if we move the threshold, you can see here as 0.2. So that means like 20% of those are going to do something. In our case, I'm going to put 0.5. So basically 50% of our clusters are going to be actually smaller clusters than this. So what we can do, we can actually add a group in the vex. We can do group underscore small cluster equals 1. Let's do split cluster. And then now if we do split, we can actually see the small cluster attribute now. Put small cluster group. So those are the one we're going to, once again, we're going to copy and paste our thing, and we're going to attribute delete this cluster. In here, we're going to put a smaller cluster size, 0.25, let's say. So you can see that this is fairly small. Those are not like just one or two, like one triangle, but those are like can be 2, 3, 4 points. So like very smaller clusters, right? And then we're going to just rename them. So we need to give them a unique name as well. So we're just going to do cluster name 2 plus we're going to add small cluster. Okay, so this is a cluster name 2. Can get pretty long. Basically, we don't have that much pieces anyway, so it's not going to be this heavy to store on disk or anything. Cool, and then now we're just going to merge them together. Alright, voila. So we have the small clusters and the medium-sized clusters in here. Now we're going to do the same thing, our unique cluster thing, and we're going to copy this file cache actually. And instead of being cluster name, it's going to be cluster name 2, and here cluster name 2. Or to call this one small cluster. And yeah, let's bake this to disk. This one can be a bit longer. You can see here we have 225,000 pieces cluster, so it's going to loop. So like that's why here compiling or for each can be very useful. We can see how fast it's actually doing. It's not doing one by one, it's actually splitting this into the different threads of your CPU. So yeah, almost halfway there. All right, cool. It's done. So now let's compare again. Cluster name 2, we have 227K, and before we had 225K. So like, you know, we create like another 2000 name based on the proximity, which is fine. Just it's not that much, but like, you know, just some. It's just a thing that can help us fix some weirdos that are flying in a strange way, and those usually are created that way. So we're going to add this one and do a small null here. We're going to do this in small cluster. Cool. So now, basically, we're not going to transform pieces this just yet. Before this, we're actually going to take the small clusters that we just created. And we're going to attribute copy based on prim ID. We're going to copy cluster name and cluster name 2. All right, so what we have. Cool. Can actually cut this connection for now. And here, what we want to do just now is we're going to, well, I guess we can say we can keep this one here, here. So now what we want to do, we want to try to extract a transform based on this cluster name 2. So if I were to try to extract transform here, this response the animated one, but instead of putting cluster name, I would put cluster name 2. And here you can see that it's erroring because we're obviously not on the good attribute class. All right, cool. So you can see here I was at, here I was at 1.502 and now at 227K. So now I have like way more saturated here, right? So, but the thing here is like if I were to transform pieces again, same piece of geometry that we had before, based on cluster name 2, this is what we would get. So we have this. Okay, I think something here is not right. Okay, we have the correct small cluster thing here. And then have our big pieces. Cluster name too. Okay. So in my test, I had something a bit more. Is it this? Prim ID. We have our big cluster. Oh, okay, yeah. Basically, this would get us the same exact same thing, but instead of doing this, we're going to give it just before we do. We're just going to give those frame here. All right, so here we're going to give this one this big cluster anim. We're going to attribute. We're going to move it by cluster name. And here, obviously, cluster names equal name. So all right, and then if I extract this and retransform it back, I have the exact same thing. What did I do? The cluster anim. So the big cluster name is actually here. And now we're going to do prim ID. Yeah. That's something way more organic. If I were to do this, we're just going to rebake this cluster with a different name. I'm not going to put the big cluster name first. All right, now we have this organic thing. So yeah, basically here the idea was that is going to do this type of organic interpolation for us. So we would go directly from here. Sorry, to this. Because of the cluster would be into different island, it wouldn't know exactly which one to pick up, and so we'd actually get deformed this way. So yeah, obviously here feels way more organic and more high res to ultimately have those edges kind of start to shred. So yeah, I think we can do a flipbook, and now we're going to start to make this even cooler. Okay, cool. So now basically what we're going to do is add a bit more dynamic into it, and we're going to break those pieces even more apart. So here, right at the back, you can see that there's now this operation, the extract transform here, is going to take a bit more time. And so basically here, well, it's basically like, you know, this point deform here and this extract transform, both are going to take a bit more time to compute. So basically what we can do, we can just directly create like another file cache. So actually I'm just going to grab here the one of the file cache we already created. I'm going to switch back to manual. Time dependent cache time. So here we have like our own frame range, the whole frame range back to $OS. And we're going to call it this time we just got it extract transform bake. And yeah, we can just bake this into disk. Yeah, that way we'll have something a bit more reactive in the viewport. It will be able to scroll a bit easier into our scene. So I'll let this finish and then I'll come back to this. All right, cool. So now it just finished. All right, so now I can see I have spawn clouds. And if I just transform here, everything should be pretty fast in the viewport. Yeah, we can actually scroll through it, which is pretty cool. All right. So yeah, first thing that we're going to do, we're going to try to destroy those edges a bit more than this. To do that, we're going to do something based on neighbors and proximity at rest. So basically, we're going to look in the first frame and try to find neighbors that are on different clusters. And we're going to calculate the distance between them, and then we're going to compare the distance over time. And when this distance is going to be higher than a threshold, we're going to activate this piece. So in order to do that, we're just going to do a very simple very simple pop network. So here basically we have those points. So each point represents our cluster 2. That's like the small clusters. And those are actually moving our pieces for us. Great. So now I'm just going to go on the first frame. And this is where I'm going to try to find those other clusters. So basically what we can do here, we're going to find neighbors. So to do that, I'm going to create a list because I'm going to use near points with S, not just singular. I'm going to look for 0 in this context, P, and then I'm going to create 2 channel fluids, so the max distance and the channel integer max points. I'm going to open this a bit more, and of course, just to close this properly. Cool, max distance, we can put 2.1 and we can put 80 points, see if it does something. Cool. So here, like the what we can actually let's do a small test. So we're going to create like just an attribute called test, and we're going to put neighbors like this, and then we're going to put 0 inside here. So if I were to add all the other attributes and just display test, it's super easy. We can see that every point returned is on self. The reason why is because obviously if you compare this point, it's going to say, well, I'm my closest neighbor. So that's why I arrive in the first position. Then the second closest neighbor, you can see that those are different points then. So here, potentially, if we have a look at point 17, 178, 142. So I can just go to blast this one. It's probably going to be either 95 or 29 here. So let's just actually check which one it is. So it is 29. You can actually see that it was this 29 that is the second closest. So basically, yeah, this is the information that we have. We have this list with the point number of all the closest neighbors that we have. Until there, we're all good. We're just going to store something called neighbor points, and then we're going to put it as -1. I'm going to explain this just after. In the meantime, we're going to do a for each in this in this list, so neighbors. So I'm going to declare something called I for the increment, and I can just simply type neighbors here. Close that, and this is my for each. No errors, so we're pretty good. Basically here the ID is to compare the cluster name. So that was actually something that we forgot to do here. It was just copy the cluster name. So our first big cluster thing. So but it's okay, we can still do it here. Probably will be a bit less efficient than if we already did it, but we're just going to type cluster name based on cluster name 2. And so now we can see that we have it. Okay, but it's actually not too bad, and like this one is, we're not time dependent anymore, so we're all good here. All right, sweet. So basically now, like, we have those. Let me do a color, and I'll try to explain. So let's do a go random from cluster name, and I'll let cluster name 2. So basically here the idea is we're going to look for neighbors, right? And we're going to try to see if those neighbors are into a different cluster, the first cluster, not the smaller ones, because they're all different, obviously. So we're going to look out for, we're going to try to find the data of the name of the neighbor, right? We're going to call this name neighbor, and it's going to be points 0 and we're going to look for this cluster name 1. So here, and then we're going to put I for the increment. I close this, and then I'm just going to do a small comparison, and I'm just going to say if cluster name is not equal to name neighbor, then you're going to put a color just so you can see it, and we're going to break it. And actually, we're going to remember here I put -1. -1 is just to say usually that returns a negative value, to not just like mismatch it for like if it was actually pointing to 0.0. So here I would just put neighbor points equal I. And then I break it, meaning that I will not look for other stuff. So like the for each would actually end here. And so now you can see here that we have a bunch of points, and you can see that the points are in the middle of a big cluster. They stay white because we're not giving enough points here. So basically, this will kind of define how much points are we going to run the for each on. So obviously, the more points you have, the longer it's going to take to compute. Here we have like a relatively pretty low point count. It's like 200k, so it's not too bad. But yeah, the max distance. So it's going to look for radius, and then like the amount of points at 80 is going to stop. And so like we know that this list can't go higher than 80 here. Cool. So I'm just going to name this angle, find neighbor points. And then I'm just going to record the distance between the two. So to do that, I'm going to do the length, or actually I can just type distance. So either like it's the length of the two vector subtract, or there's a distance function directly in the X. So you can type distance and you do P and you look for the position of our neighbor point. So it's going to be 0. We put P as well, and then we're going to put the neighbor points. So now we store this distance, and we're going to store the neighbor point as well in an attribute. So you can just put an integer here. I'm going to go equal neighbor point. So this is basically the closest point number that is not itself, and that is on a different cluster, right? So now we can see for 0.0 is going to be 136,429. So yeah, which is different than the tests here that they did, because potentially those were like in 0.0 and 1,554,000 were like in like the same cluster, so that's why I didn't return it. I can bypass this test. We don't need it anymore. And so now this is where we're at. Cool. Here we're just now going to copy back the position. So this is the exact same point count. So we can just do attribute copy P. Nice and easy. Here in this case, I'm going to compute the velocity. Compute vel, I can check. Do we have vectors? Yeah, here, so all good. And now basically we're going to activate those points. So we have the distance, which is the distance at rest, and now we have the numbers. So we have the point numbers. So we're just going to calculate again the distance between the 2 points in motion, and we're going to compare it to the rest distance. So I'm going to create like another attribute triangle. Call this one activate. And so I just put like float called new distance. And this is going to be the distance between P and, do the exact same thing that we wrote in here. The only difference here is like, we need to take the attribute in this case. And now we're just going to do a small thing, which is say if obviously this guy is not equal to -1, because all the -1 we never want them to activate. And basically we're just going to say if this new distance is higher than our distance attribute here, so distance at rest time a multiplier, then let's make it yellow. All right. Obviously here by default it's going to be 0, so like the typical range of this that you want is going to be between 1.1, 1.2, and 3 or 4. So here you can see that everything is red, nothing is getting activated, but then, boom, I can see some activation stuff happening when they're going to start to detach each other. So here in this case, I think you can see that it's a bit sensible still, so I can increase a bit the threshold, and you will see that it will start to activate a bit later when they really start to be far apart. Cool. So now what are we going to do with those? So we're going to create a pop network. And we're going to make them dynamic. In order to do that, first, we need to change our type of source. So we're going to switch to old points, right? Then the birth as well is going to change. So we can right-click, copy parameter on this start frame, and we just do a if $f equals this on the first frame, do 1, and the rest. I don't want to continue spawning particles every frame. So you can see that here now, like it's just on in the first frame and then it's switching to 0. We're going to remove this guide. Okay. So that's it. We have this. Obviously here, nothing happens and it's normal. You would expect them to potentially, do we have some velocity here? Did we lose the velocity? No, it's there. Okay. So the thing is, like, we don't even have the velocity push because on the first frame we don't have any velocity. But it's okay. What we're going to do now, we're just going to make sure that we're storing not just in the color, but we're actually going to store this as an attribute, right? So active. What I like to do as well is storing the active frame, and I'll explain this a bit why. So here I'm just going to put like a very big number, and I'm going to call this active frame minutes. All right, cool. So now basically we're just going to do a pop wrangle, and we're just going to update the the position of the P. So we're going to do P equals 0.1 P to num. Same for V. And to do, could copy this. And here in the inputs, we can put first context geometry here. So now we can see that now we have our moving particles, which is, is something. We did the initiation part. Another thing is like we need to also update the active. So I'm going to do the exact same thing here. Except I'm just going to say active equals active and giving the same inputs here. First context geometry. And just to visualize that we're actually copying the value, we're going to do this group active equal 1, and we're going to put it as green, let's say. So let's go a bit further down the timeline. All right, and so now it seems to be working. We're updating the active here based on what we have. Cool. So this call this update active, update P and V, and then check check active. Cool. So the thing is, we would want now to not update the position when they start to active, right? So we're going to do this group for active equals 0. When they're not active, we want to actually match the animation, but when they become active, we don't want that. Instead, we want to maybe put a pop wind for the active. And for the group, we're going to do active equals 1. For the wind velocity, we can just put like something like 1, and we're just going to see if it does something here. All right, that's right. All right, so already now we can see some very fast moving particles. Something's happening here for the green ones, which is good, I guess. Just a bit weird behavior that they have. So for some reason they're going into this direction. Oh, okay. And I see why here we forgot to just put V for the velocity, so it was actually putting the position, the velocity. And now we should have something that makes more sense. So I would expect now to see the green particles, just start to detach and go from left to right because we put like a force on the x-axis in the positive part of the x-axis. Okay, so it's kind of working. Like now we can see the activation, but the thing I don't see personally now is I don't see the wind. So maybe something is wrong with this. But you can see that there's something pretty nice about it that like it would still get the velocity of it, and like we would get like pretty organic disintegration. Actually, if we even were already to, the thing I don't know why is because I didn't put an at. So now it's not looking for the right group. But anyway, we can actually test this for to transform pieces here. And we can actually switch from the dynamic to the non-dynamic. So you can see there's something different here. So first, the first thing that is different is that we're not updating pivot and the orient of those pieces. So let's do in added position. Let's actually add those attributes. So first we can do the pivots. So the pivot is going to be point pivots, and for the orient, so it's a quaternion, so we need to put the letter P, orient, and here we're going to look for orient as well. Okay. Now let's see if we have something that makes a bit more sense. Let's wait a few seconds here. Okay. So here, let's just try to keep the attributes that we really want, just to make sure there's no. So we're going to switch to delete non-selected, and we're going to keep pivot, orient, cluster names, and to keep the ID, and we can keep the neighbor points. That's about it. Okay, there's still something here that doesn't seem to be working quite as right, and it's actually here that is the main problem. Here we're updating the position, but we're not updating the orient and the pivots. So we just need to update those. And now if I press refresh, okay. So here now we can see that on the arrows that are not activated, you have the exact same pivot and rotate thing. So here on the first frame, we don't see quite a difference. We have a few stuff here that looks a bit different here. But you can see here like that we already have those clusters that start to detach. So let's go a bit further now the timeline and see how it looks basically. Okay. So if I switch back, you can see here that we had like some pretty big gaps here and some still pretty clean edges. Where here now we're starting to continue the tearing apart of those. Cool. So I think that's working pretty nicely. Now let's try to see how it looks with a crazy wind. So here, like we're going to adapt, just add the at. And now we should see some very fast moving cluster as soon as they're activated. Obviously we'll tone this down, but let's do a small flipbook and actually see how it looks. All right, so this is what we have. Obviously, way too much, but now we know that this is working for yeah, a bit more or less slow-mo, more extreme thing. It could have been a thing. But yeah, like here, way too much. And also, so like the other thing is like they all the pieces are actually going at the same speed. So we want to randomize that. So to do that, let's go back here and in the popnet. Now we're going to click on this toggle, use vex expression. And here, so there's two different things. There's the wind velocity. So here is going to be, if you actually hover your mouse here, you can see that those, they tell us the name of those parameters, right? So here, wind x, so wind.x equals rand ID times, then we can create like our own wind amount float thing. So here you can see that now we will obviously, they will have all the particles will have between 0 and 1 times this wind amount. So for the wind amount, I'm going to put 0.045, and we can put a bit of noise as well. So this is going to be in the amplitude. So it's called amp. So I'm going to do amp. Cool, same thing. Plus, let's say C dot for this one. Times noise amplitude. For the scroll size, I'm going to reduce it because obviously here the scale of the scene is very small, so I'm just reducing this. For the wind amount, for the noise amplitude, I'm going to put the same thing, but just with a different seed. Cool. So I think now we should have something a bit more reasonable, you know? And yeah, that's about it. So now the only thing that we need to do is we're going to update our active frame thing. So we can put pop triangle here, and we're just going to do if active equal 1, so double equal here, and we're going to do and. So to do that, we're going to do this one, and we're going to do an active frame higher than 10,000, let's say. Then we're going to do the active frame here. So why we're doing this one is just basically we're going to say if this is your first time, like, you know, we put like a very big number in the initial state. So if it's your first time that you're getting activated, then you're getting frame. Otherwise, we're not re-updating the active frame here. So let's just do update active frame, and then just make sure it's working. I go here. Cool. Let's see if we have some. Let's actually take it as well. And we can see that here we have some frames are 18, 19, 20, 22. So like the active frame thing is actually working. Cool. So yeah, once again, let's just take our file cache and let's cache this to disk. Always simulation, and we're just going to do $OS, and we're going to do Disintegration, pop sim, and let's cache this to disk. It's going to be fairly fast to do. It's not like a big sim. We're just like updating position of points, and then yeah, for now that's basically just what we're doing, and just storing when they get activated. So yeah, let's run that, and we can potentially do a playbook just after. Okay, so this is what we have. yeah, looking pretty nice. It's organic. Now we can feel it still continue to be destroyed over time. Great. The only thing that we can improve here, we can add a bit of rotation as well on those clusters over time. Then we're going to extrude them to give them thickness, obviously, and still reattach this simulation on top. And after we're going to do the circular. So yeah, exciting stuff.